Okay, so what are we talking about? We got to full MD simulations last class, okay? So things are still based around F equals MA, but we actually had some forces in our system. And what we saw was that it was actually pretty easy to have a system of a non-ideal gas, so that is the gas particles were interacting. Cool. This raised some questions about what to do next. There's other features like we need to control the temperature somehow. So we started to talk about the thermostats. Okay. Last time we talked about velocity rescaling thermostats, and we showed how we could get them to work, and then how we could have still some fluctuations in them, but it still wasn't exactly a proper canonical ensemble. Okay. So I'm just going to mention one, just so you know the word. There's the Noisy-Huber thermostat. It falls under this category and actually gets the fluctuations going. Okay. This is done by basically writing the Hamiltonian in your system and including an extra term to account for our thermal coupling. Okay, we're not going to look at the details of this, but just so you're made aware. Then we mentioned there's another way to go about things, which is a stochastic thermostat. And the idea behind the stochastic thermostat is basically modeled directly off the idea that your system is somehow connected to a thermal bath. And what does a thermal bath do? Well, a particle from your system will collide with this thermal bath. There will be an exchange of momentum. So let's do that exchange of momentum. And so the first MD thermostat proposed was called the Anderson thermostat. And the idea behind this is that you have periodic collisions. And the frequency of those collisions are selected from a Poisson distribution. Okay? And when you do have a collision, what you do is that you pick some particle at random. Okay. And you assign it a velocity from the Boltzmann distribution. Okay, so this is a way of kind of modeling the interaction with a heat bath, because this is more or less what happens when you interact, right? Exchange of momentum, some particle. Cool, fair enough. So this was, in fact, the first thermostat used in MD simulations. Yes?
Doesn't this mean like you have a particle moving at some speed and then we just instantly change it?
Yes.
Kind of thing? So we get kind of weird behavior off that?
Yeah, what's wrong with this approach? What does that violate? Yeah, but we have thermostat, so that's okay. We're trying to violate conservation of energy, right? Conservation of momentum. Conservation of momentum. Okay. The problem with stochastic thermostats is that they violate conservation of momentum. Okay, and so if you have some code that's looking at dynamical transport quantities in your system, they're going to be affected by you violating conservation. What's the notation there? PFT. It's just PFT, yes. Just probability of a collision.
Oh, I see. Yeah. And so typically, with something like this, would you just need a massive number of particles to kind of offset that? I think, or?
No, because you have a more massive number of particles, you have to scale frequency at which you're colliding too, right? So, yeah.
Fair
So there's another stochastic thermostat, okay? The Langevin thermostat. The idea here is basically to modify our F equals MA equation to include further terms that will do the thermostating for us, okay? And in about 10 minutes, we're going to start getting into the nitty-gritty about this approach, okay? It has a lot of applications for us in this course. Okay? So as has already been highlighted, the problem with stochastic thermostats is that they don't conserve momentum. Okay? And so things like if you have some hydrodynamic flow, this kind of thermostatic is going to destroy your hydrodynamic. Okay? Because they're just randomly taking things and assigning velocities. Cool? There is a way to have a stochastic thermostat that does preserve local momentum. Okay? And this is the dissipative particle dynamics. That's a DPD thermostat. And we will come back to this thermostat hopefully later in the course when we talk about mesoscopic fluid models. Okay? Because obviously, if we're doing fluids, we need to have a momentum conserve. So this is a thermostat thing. Yep, it's still stochastic, but it locally conserves.
It's not stochastic.
Yes, this.
And it does not conserve.
It does. Cool. Okay, so this is just kind of an overview of how we can thermostat our system so we can keep our temperature under control. We also talked about an ensemble in which we had a constant temperature and also a constant pressure. Okay, so in this case, we don't need a thermostat, we would need a barostat. Right? And I don't want to go too deep into detail of this. I just want you to be familiar, similar ideas hold here, but what might be an easy way of controlling the pressure in your system? Modify volume. Modify volume. You can actually allow your system to shrink or grow a little bit. So you make a calculation of the pressure in your system, and then you scale your volume according to that. And in fact, you can go back to your Berenson thermostat, where we had our temperature changing as a function of time, and it was proportional to the difference between our current temperature and our target temperature. We do the same thing with pressure. Okay, so we can scale our volume at a rate that's proportional to the difference of where we are and where we want to get to. Cool? Okay. So I really want to talk about this Langevin thermostat, and in fact, Langevin dynamics for the next little bit. Before I get there, I want to try to come up with a way of motivating what we're going to do now. Okay. And so to do that, let's look at two different types of motion. Okay. Okay, so for the first type of motion, let's look at a single particle. Okay, so we're going to tag a particle. In the simulations we've had so far, okay, the interacting gaps. And let's watch it in the dilute limit. So when there's barely any particles. Okay? And so this is the same code we've seen previously. I'm just changing n. Previously we had it at 100, but now I'm going to change it to only there being 10 particles in the system. Let me load the trajectory file a second. All right, so this is what it looks like in the dilute limit for our whole system. Okay, and let me change one more thing. Okay, so they have different colors. So here's what it looks like. Okay, and now what I want to do is just look at one of these particles. So we'll just hit the thing. Thank you. Okay, So let's just tag one of these particles. For simplicity, what we'll do is we'll just take the first one. Instead of selecting all, I'm going to take index 0. Okay, it happens to be this guy here. So this is from the start of time. It starts with a big velocity, and for a long time, it's keeping that velocity, it's just bouncing off the wall. And then it undergoes a collision, and there's an exchange of momentum, and it has a different velocity. Okay? But basically, if this thing wasn't in a closed system like this, you would just see a particle moving at some constant velocity. You would have ballistic motion. Okay? You could well describe this by first-year physics. Delta x is equal to v delta t. Okay? For the majority of the time. And then very rarely it would have these collisions. Okay? So this is the kind of ballistic motion that we're used to. If you throw a baseball, if you're driving in a car, if you fire a cannonball. Cool. No mysteries here, right? But now let's look at when we have a lot of particles. Okay? And again, remember the particles are interacting. So I'm going to run the same code again. But now I'm going to have 500 particles in our box. Okay? There's going to be a lot of them. Let's load up the trajectory.
So every time a particle hits something, it changes.
Yeah, but when it hits a wall, it's really trivial. It's only when it hits other particles that you actually see a real change. That's when momentum is changed and something different happens. Okay? And if we're in the dilute limit, this happens pretty rarely. Okay?
But in this example that you just showed us, is this particle hitting other particles?
So if you watched it, it hit one other particle.
Okay.
It had a big velocity kind of going back and forth like this, and then it hit another particle, and it actually had much less velocity.
All right. Yeah.
Okay? But that's it.
But
It only
that's
had
not,
one
it
collision.
didn't slow down because of the hitting the wall.
No. Okay. Alright, so we got a lot more particles in here. Let's color them by index so it's a little easier to discriminate them. Let's start the simulation. Okay, so this is just the interacting particles in a box that we had last time. Okay, but again, let's isolate one particle and let's see how different the motion looks. So again, I'm going to go from showing all of them to just selecting the first one, so index 0. All right, now what do you see in the motion? Does this look like ballistic motion? Yeah, okay, very different motion. It's not like we have a particle going at some velocity that occasionally gets a hit and then just has a new velocity and travels for a while and then occasionally has a hit, right? Now, it's almost always, there are very short times between collisions. So it's very hard to say at any time which direction this particle is going, okay? It's constantly changing its direction and kind of doing these jumps in different directions. Okay? This is a different type of motion. So if we call this ballistic, what's this? What motion is this? Anybody know?
Diffusion?
Yeah, it's diffusion. Okay? And we'll be talking about this a lot in the next couple of weeks, about the difference between ballistic motion and this diffusive motion. Okay? Diffusive motion has very different characteristics. Cool? Everyone with me? Okay, so this kind of, this is also called, as Martin said, a random walk. Okay?
Right. So the difference between ballistic and diffusive is, for ballistic, it takes more time for the particle to change directions.
So Ballistic is only the time between collisions. Okay? So ballistic means you're basically traveling at a constant velocity. Okay? And then you have a collision and you get a new velocity, but then you travel at that velocity. Okay? So each one of those legs is ballistic. That collision step is not. Right. Okay? Cool? The ballistic means you have a certain direction and you're going there at some speed. Right. Okay? So it's very defined deterministic motion. This is not. This is totally random. Okay? You want to put money on where this particle is going to be at the end of the simulation, we'll take that bet. Okay? Not even that will bet. So you know it's a bad bet. Cool? Any questions on this? No? Okay, so here's my question then to you guys. In order to get that ballistic motion, I needed to simulate 500 particles in this box. I didn't get it when I only had 10, right? But what if I was only interested in that one particle that's bouncing around during diffusion? Okay? I want a model, a simulation approach, in which I can have particles diffuse around without having the need to be in a sea of other particles that provide all those ramifications. Cool? So instead of doing an MD simulation with all these particles and just isolating one of them, I want to do a simulation with just one particle, but still have that random walk diffusive. Cool? So instead of explicitly simulating all these particles, I want to only explicitly simulate one and include the effects of the other particles implicitly in the equation of motion for that particle. Sound good? Okay, so we're starting our next topic then. Can you hit like the end of the Thank you.
You just randomly heat up one of the walls, and whenever a particle hits it, you get an increase in velocity. And if you just turn them off, the wall off and on, so you increase like a randomness or change walls are heated up.
Yes.
Randomness?
Yes. So that's useful, but what you're going to get then is you're going to get spatial dependence in your temperature distribution, right? So if it's that one wall where it's very hot, and when they actually hit there.
Oh, okay, yeah. There's going to be a collection of high velocity particles. Right there.
Yeah,
Okay.
because it takes some time for that to dissipate through the system. So that may be what you want, but maybe not. And so that's why, if it's not, if you're like, no, I just want uniform temperature on average with no isotropic, right? Then what you want to do is randomly select. Cool? Okay.
Sorry, one more question. So these motions depend on the number of particles you have in your box?
No, so to clarify again, okay, between collisions, we could consider this to be ballistic motions.
Right.
Okay. The question is, if you're in the very dilute limit, your system almost always looks like it's ballistic motion.
Right.
There's very rare collisions. If you're in the very dense limit, then the actual little ballistic pieces between collision are very short, small, and so instead it just looks like it's randomly jumping off. Okay. Yeah. But what I'm trying to do is really contrast diffusive motion from ballistic motion. It's very different. Okay. And we're going to talk about that till you guys are sick of it. So. Let's talk about a stochastic differential equation. And to be specific, we're going to talk about the second order Langevin equation. So this is topic 2 in the course. 1 was MD, 2 is the second order Langevin equation. Topic 3 will be the first order Langevin. Okay. So the reason I'm doing it in this order is the following. Molecular dynamics is very easy to motivate. It's first year physics. It's just F equals MD. Okay, that is it. You get an acceleration, you numerically integrate to get velocity, you numerically integrate again to get the new position. Okay? I want to take that same idea and I want to develop a new simulation approach. Okay? And so I'm going to modify F equals M. Before I do that, I want to introduce something we've talked about a bunch of times and formally introduce it. This is the idea of the equipartition theorem. Okay, and what the equipartition theorem states is that total energy in your system is equally shared between all different forms of the energy. The average potential energy in your system equals the average kinetic energy. And so if we look at the average energy of a particle in our system, it is kT in each degree of freedom, and that's shared with potential. So we basically have 1/2 kT per degree of freedom in our average kinetic energy. Okay? This is the equipartition theorem. We're just going to take this as given. This is kind of a axiom of the universe. Okay? There are ways you can make sense of it because sharing the energy can lead to the exploring of this number of states. Okay? Cool? Everybody okay with this? Yeah? Because remember, kT is just a measure of the energy in our system. Okay. What is the kinetic energy equal to? First year of physics.
1/2 mv squared.
1/2 mv squared. Okay? And so we can solve that the average squared velocity, okay, is equal to d over m kt. Good? The dimension term, so it could be 1d, 2d, 3d. Okay. Yeah? Is that right with people? Okay. And in fact, we can write that the square root so that we get the units right. Okay. Root square velocity. It's that. Cool. This is the result we're going to need and what we're going to do now. All right. Cool. All right. So let's do the thing I alluded to. Let's take our F equals ma, write it like this. F equals r double dot. So the acceleration is the second time derivative of the position. And we're going to consider a single particle, okay, for now. And so for a single particle, what was the net force on the particle? You have a particle alone in the universe? 0, there was nothing then. Okay, that's why we had an acceleration of 0 when we did our first ideal gas, right? Okay, now let's not have the force equal to 0, but let's include some terms in our equation of motion, okay? And what we want these terms to do is to account for the effects of other particles. So let's take one particle and pretend it's in a sea of other particles. Another way of looking at this is saying, let's take one particle and consider it in some kind of solid. Okay? Take an ion in water. Okay? What is the effect of that water on that ion? There are two effects. Not people in my lab answer. So when you saw that movie and we went from the dilute limit to the high density limit, and we were tagging one particle, what happened? What do you mean by that?
Particles going all over the place.
Yeah, right? So all of a sudden we didn't have a particle that was just traveling in straight lines of velocity anymore. It was doing all these crazy jumps, okay? And why was that? Because there's so many other particles there that are giving it kicks in all different directions that it's like there's a random force acting on this single particle, okay? So what do we need in our equation of motion? We need a random term. And that random term is going to give us, it's going to model these thermal kicks from the other particles in the system that are in contact with them. Cool? Okay. Anything else? Is there anything else we have to account for? And now making the effects of the solvent implicit in our equation.
If an ion is charged and it's interacting with water, you have to include it force.
Yes,
Yeah.
it's a very good point. Okay, we should account for electrostatics. Very good. Okay, we can add the electrostatics later as a force component. Okay, and you can, if you're going to include the water implicitly, you can do field stuff and just include a different epsilon in your calculation of reservoir weight charges to account for the polarizability of water between the two charges you're considering. It's a great point. I'm not going to do that. Okay. Anything else?
Do you care about the temperature?
Yeah. Do. You're getting close to it.
I don't know, my guess is.
So if we have a particle alone in the universe, right, and we apply some force to it, it starts from rest, it starts to accelerate, right? If it's alone in the universe, if you were to plot its velocity as a function of time, what would it look like? It would just keep increasing, right, with whatever acceleration applied to it. If you now put that particle in some medium, like water or even air, now what's it going? Does it still increase to infinity? If you drop a watermelon off of the CN Tower, and you don't do this, if you drop it halfway and you drop it from the top of the CN Tower, is the velocity bigger when you drop it from the top? No, because it reaches terminal velocity, right? There's a drag force that scales with the velocity. So when you start going really fast, your drag force is as big as your accelerating force, and you have no net acceleration. Okay, we have to include a damping force. Cool. Now we are always going to be considering the low Reynolds number here. Okay, how does the damping force scale with velocity at low Reynolds number? Anyone remember? I know because I'm also teaching first year mechanics. Linear in the velocity. Okay. And so we could write this in terms of just R like so. Okay. And so this is our new equation of motion for the particle. All right, so including the effects of the solvent implicitly in the equation of motion. This way we don't have to simulate 500 particles. We can just simulate one, and we can still get that jumping around. Cool. So of course, this also raises questions. What's this? And what are the characteristics of this? Okay? And so we're going to be spending the next little bit exploring that. Cool. So we have our work cut out for us because this is not a regular differential equation. Okay? And I don't mean that it's a partial differential equation, because it's not. There's something different about this one. What's different about it? Yeah, it's got a random term. Okay, so this is what's called a stochastic differential equation. Now, when we have a differential equation, what do we usually do? We just try and look for solutions that we plug them in, right? We take a good guess after years of doing math. and then we tweak the constants to make it work, plug it in there, and we get the answer, right? And if it works, we know we're right by the magic of uniqueness, right? That's going to be hard to do here because we have this random term, right? Which, by definition, is random. So our usual methods aren't going to apply here. Okay, we're going to have to be a little bit more tricky about how we go about solving this. Okay, and so I'm going to show you some of the ways we can go about using what we know about the noise to basically get rid of the noise term so that we can still get a solution. Cool. And we won't get to it, but we will make the connection later. That formally, there is a way to go from a stochastic differential equation to an equivalent partial differential equation. Okay? There's a formalism for that. And we will just look at the results of those later. Okay? Again, because I won't focus on the simulations. Okay, but first let's just look at how we might be tricky about finding a solution for this. Well, to proceed with the solution, let's make our life a little bit easier here. Let's just make this a first order differential equation. Let's just solve it in terms of D. Okay, a couple details to note. This guy here is our damping term. Okay, and Stokes' law tells us that this is negative 6 pi eta r v, where eta is the viscosity of the medium, and r is the radius of a particle. So this is the case for a sphere. Where is the radius? Okay, so our damping term zeta is well defined by physical parameters. Cool. Hopefully you've seen Stokes' law. Just a sphere moving through a fluid. What's the damping force? Okay, you can do the calculation. Taking fluid dynamics now. Cool. We're okay with this. Yeah. Okay. So how can we go about solving this differential equation? Well, it's too bad we're in this room today. Going to be erasing a lot. But let's slightly recast our equation to be v dot equals c over, or sorry, zeta m v plus 1 over m random term. And so this is our friction coefficient, and this is our mass. And it's very common to define that as gamma. All right. And this is an acceleration. This is a velocity. So what are the units of gamma? What are the units of acceleration? Meters per second squared. What are the units of velocity? What are the units of gamma? 1 over second. Okay. What's the inverse of a time? Right, it's a frequency. Okay. Gamma is your clip. Right? Okay, that's nice. We've rewritten things a little bit, subsumed some variables into each other, but we haven't gotten any further. We still have a differential equation that has a random term. Okay? So here's what we're going to do. we're going to take this differential equation. We're going to take the inner product with the position vector. And I'm going to take this over to the other side.
We just think of the way.
We brought it over to this side.
Oh, right, each side of the
They're-
Is it equal size?
Oh, sorry. There we go. Cool. Okay. We still don't know anything about this term. Okay, because it's random. At any point in time, R could be some number. We have no way of knowing. Okay. But we might know something about the character of this noise on average. Okay. So let's just take the average of everything. Cool. Gamma doesn't have to go inside the brackets.
Just an average.
No, that's a constant. That's, remember, this thing is basically just 6/8R,
Oh,
right? And it's just mass. It's just a number. Cool. Now, do we know anything about this term? Anyone want to take a guess?
0.
Yeah, why is it 0?
The position is independent of random.
Exactly. Okay? We're taking our noise to just be some perfect white noise source. Okay? The random kicks of these other particles don't depend on the position of our particle. Right? So on average, if you take the dot product, you can get some large negative number, some large positive number, some small negative number, some small positive number. Okay, there's no preference for any of these, so they all will cancel each other out, and your average will be 0. There's no correlation between the position vector and the noise. That seems sensible? Yeah?
whole life cycle is zero.
Does that make sense? Yeah? So this is entirely independent of this guy, and when you take the dot product between a whole bunch of them and you take the average, you get 0. Cool?
So small r and big R, then you're in. Now you big.
Yeah.
Oh,
Cool? On average, the average, right? Okay? Because at any point in time, they can, right? Right. You have position vector according to your origin looking like this, and that might be where your random kick is. Okay? But on average. Cool? Yeah? So we can now say this is equal to 0, and we've gotten rid of our noise term. So there's hope after all for progressing with this. Which is, cool. Now we just have to figure out what these terms are equal to. Okay? So we can rewrite our differential code. Okay? So we're going to use a couple identities. Okay? So let's look at the time derivative r dot r, which is the time derivative of r squared, which is the time derivative of 2r dot. Cool. So this means r dot b is equal to 1/2 d dt r squared. Yeah? All right. Now let's look at the time derivative of r dot v. We have to use a product rule here, right? Do we take the derivative of the first term multiplied by the second, what do we get? Yeah, so what's r dot? Well, we take the time derivative of r, which is,
Oh, the derivative of r is v.
yeah, and v dot v is v squared.
And then Ra.
Yeah. Let's keep that as d dt v. Okay, and so we can, this means we can write r dot v dot is equal to d dt r dot v minus v. But we solved for what this guy was equal to up here. Okay, so we can use that result in here. So this means we can say it's equal to 1/2 second time derivative of r squared, and we still have our minus v squared. Cool. It's cool with everybody? Because remember, our new differential equation has this term in it and this term in it. Okay? It also has that gamma in it. So we can now use these identities to rewrite our differential equation into yet another form. Cool? Everybody with me? Okay, let's do that. So I have to erase these. And what you get is we have the r v dot, which is the second time derivative, r squared minus v squared, and again that's an average, plus gamma 1/2 d dt r squared equals 0. Ooh. Well, we have these massive averages around everything, but it's really only around these arguments, these variables themselves, that we need to worry about the average, right? Obviously not the operators or the constants. Really, we have and let's, sorry, at the same time, let's rewrite it a little bit. So we'll get rid of this 2. And let's keep all the r terms on one side and pull the v terms to the other side. How's this for people? All right. So this suggests something. Solve this, what might be a and b?
Well, we already solved the average of v squared earlier today.
Yes, very good. So that's one thing. We can pop that into here, and let's do it in 3 dimensions. Okay. We get 6 over m kt. All right. And then let's also define U equals the average R squared. Cool. And so now we have U double dot plus gamma U dot 6 over M KT. And let's call that C. So we can reduce it this differential. Cool. So we've gone from a crazy stochastic differential equation to a nice ODE here. If we can solve this for U, then we can recast it in terms of the average R squared. Okay. All right. How do we solve the differential equation like this? Anybody have any ideas?
What
What do you do?
like if we're transform it,
We don't want to do that. Okay.
we have to push it.
What were the words you were saying before? Well, we can't do it first order the right way. Yeah, Brett, make that.
What was I saying?
Could you just have you're saying measure. We have something like this. There's two types of solutions. Right? Yeah, you have complementary solution and particular solution.
Oh, yeah.
Right? So you can generate the secular equation, right? R squared plus gamma R, the characteristic equation, R squared plus gamma R 0, right? Or the complementary solution. What's the solution to this? U equals
0 or negative gamma.
well, you can solve that R equals negative gamma, 0 being the trivial solution, right?
Right.
What does this tell us about U then?
Maybe we shouldn't use R for that.
You're right. We probably should use something else.
Oh, yeah.
So this is our characteristic equation. What does that suggest about U? Pardon me? Nope.
Exponential.
Exponential. Right? So our complementary solution is A times e to the negative gamma t. Cool? Ringing bells from the depths of differential equation courses. Yeah? Okay. So this is the particular solution. And again, I have to erase this stuff. So any ideas for the particular solution? Well, it's pretty easy here, right? Because we just have this constant on this side here, right? And so we can make a good guess. The particular solution is probably just going to be linear. And if we pop that into our differential equation, what do we get? We get 0 plus gamma b equals c. And so we can solve that b is equal to c over b. Yeah? Okay. And so what does this tell us? Well, our particular solution, u, as a function of t, is going to be equal to c over gamma t And just for a moment, let's plug in what c is equal to. We get 6 kt over m gamma.
Then we add these solutions together.
Yep. So u of t then is our complementary, which recall is the exponential plus the particular. So the constant. Cool. Is good with people? Well, remember what u of t is. That's just the average r squared. Okay, where r now is our position.
This c at the end is not 6 over mk.
No. So that's here, right? Yeah. Cool? We good? Yeah? Okay. So to proceed any further and figure out these constants, okay, our A and our C, second order equations, we have 2 of them. We need, what do we need? Initial conditions, okay? So for the initial conditions, what we're going to do is take delta distribution so that all the particles are at, they start at the origin, okay? R would be equal to 0. Cool?
The delta distribution, all of the averages are all at 0.
So all particles
The average.
are at the origin at t. No, all particles at t equals 0. The initial conditions, right?
Oh,
We're going to start them all at the origin. Cool?
There's the A plus B equals 0.
Yep, exactly. So we get A plus C equals 0. And so C is equal to negative A. Yeah, we're all right.
Isn't it typically a bad thing to shove all the particles in the same position?
yeah.
Like if we give all these things a delta distribution, like isn't that initial condition kind of broken by definition?
Yeah, it's not
We're not going to put them all
No.
together.
No, no, because remember, ultimately we're interested in, so it's a very good question. Ultimately, we're interested in just a single particle, right? We
So
don't want to
that's-
simulate a whole bunch of particles.
So if that single particle that's here.
What am I talking about, having a whole bunch of particles?
Just look at the running around that one.
Yeah,
Oh, I see what you're saying.
right? So I'm going to simulate one particle, it's going to go all over the place, okay? Well, I can do that multiple times, okay? Multiple different trajectories. And if I average over all of them, any trajectory starts at the origin. Cool. But they aren't interacting, they're separate trajectories. Okay. And so this actually raises a really good point. If I say that they all start at r equals 0, then this quantity here, the average position squared, is the same as the change in the position with respect to time, right? Because if they all start at 0, these things are equivalent, right? What I'm solving for here is not the position of the particle as a function of time. I have no hope in solving for the position of the particle as a function of time because it's a stochastic differential equation. It can take any number of different trajectories in space. But what I can hope to solve is what the trajectory looks like on average. So not how far any particular particle goes into time. But if you average over a whole ensemble of trajectories, particles going a whole bunch of time, then you know on average how far has it gone in some time t? Cool. And remember, we had to do this average to get rid of the random term in our equation of motion. Okay, well, there's no mistake, because if we're trying to solve some particular equation of motion, like for one particle, well, good luck, there's a random term. Okay, but we can average over it. We can still find out information on average what is this particle. Cool. And it's even deeper than that. We aren't calculating on average how far the particle goes. Okay? Because on average, how far the particle goes, we'll see, is 0. On average, the particle is 1. Because if you have no bias in your system, you're just as likely to go left as you are to go right, as you are to go up, as you are to go down. You are out, go in. Okay? But what is non-zero is that distance squared. Okay? This quantity here is very special. Okay? It kind of is to ballistic motion what the position is. This is called the mean square displacement. Cool. The mean displacement is 0. It's pretty trivial. Okay, in diffusion. But the mean square displacement is not. Okay, and that's what this delta R squared.
You said that whoops.
Well, this, because I'm starting at the 0, I can point it to be the same delta R.
Oh, they're equal for all.
Yes. Because the delta R is just defined from where you started, right? I want to make that connection, because when I talk about the mean square displacement, you will see it written as this. Not that. Okay? And we'll see why that's important in a minute, because in order to calculate the average, we can not only do a whole bunch of different ensembles, we can also do one long trajectory and basically compare different time. So in that case, our R naught keeps moving, right? But we're only interested in the delta. Cool? Okay, so where are we? We're almost at the solution.
Don't you need it under initial condition to figure out what these?
Yep, I said we're almost on it. Yeah. So we have delta R squared as a function of t on average. So this is our mean square displacement. It's a e to the negative gamma t minus 1 plus 6 kt over m gamma times t. Alberto just pointed out, we need another initial condition, okay? So to get the initial condition, let's look at d dt r squared function of time on average. And we just went through this to get r dot v. So if we evaluate this at t equals 0, again, we're looking for an initial condition. And we want to take a guess about the right-hand side of this equation. Why?
Because the radiated or position at 0 is 0.
Yep, for sure.
Okay.
But even if that weren't true, what can we say about this experience?
Well, then you just say R and R dot R out. That's going to be 0. That means R and V are
Do you expect any correlation between your position and your velocity? We have no external force in our system. No. When you take the inner product and you average over all possible cases, you should get it.
They're not.
Yeah, they are.
Yeah. Oh, okay. Cool. Yes, you
Alright.
actually get to.
Yeah.
Okay.
If we take the derivative of this, then we get And let's just plug in that t equals 0 right away. Save some ink. So we're going to get negative gamma a plus 6kt over mb.
That t equals 0 should be outside the average, right? Because it's like we're taking the time derivative of a constant, right? We're taking the derivative over time and then evaluating the derivative at time equals 0.
Yes, that's right. So it should be evaluated at t equals 0. That's right. Cool. We just showed that this was equal to 0, and so we can solve A is equal to 6 kt over m gamma squared. And so finally, in all of its glory, our solution is the mean square displacement particle. Mondevin dynamics. 6 kt over m gamma squared e to the negative gamma t minus 1 plus gamma t.
So this represents, on average, how far the particle moves away from the orbit.
The square.
Okay. How far.
Yes, exactly. Cool. So you can think of it as starting a whole bunch of particles that don't interact with each other at the origin. Okay? Due to diffusion, they're not all going to stay at the origin, right? So you're kind of going to have this cloud of particles spreading out like this. Okay? And what you're calculating is how, if you just look at the average R, then anyone going in this direction is canceled by someone in this direction. But if you look at the square of that, then you see this increase of the mean distance from the origin square. Okay? And that is what this cool, the mean squared displacement. Yeah? Okay. Let's try and make sense of this and see if it matches with our intuition. So let's first look at short times. Okay, short times, let's expand our exponential here. T is small. Taylor series exponential. Right? So our mean square displacement at short time, we expect to follow 6kt gamma squared. Let's include first terms here. Sorry, I'm missing something. Nope. Plus 1 plus gamma t. Right? Ones cancel out, the gamma t's cancel out. And what we're left with, but the gamma squared cancel out here, is we also have a 1/2, so this becomes 3 kt over m t squared. Which should look familiar. So at short time, before the particle has had a chance to collide with anything, what kind of motion? No, before it has a chance to collide with anything. Ballistic, right? And so at very short times, we'd always expect this, and this tells us that our v here would be square root of 3 kt over m, which we can just get by the equipartition. Pardon me? Well, this is the ballistic motion, okay? So remember, moving. Particle in between collisions is just going at some constant velocity. Cool. So this, now when we increase the density, that time between collisions gets much shorter. Okay? So as gamma gets bigger, okay, you have to go to shorter and shorter times before this approximation is valid. Okay? But if you always look at short enough times, you're going to get this ballistic motion. Cool? Yeah? That's what we'd expect, right? This is what we already knew before we came into class. Okay, ballistic motion. Good. Yeah? Let's do the other limit then. Long time. What does this look like? Long time. Mean square displacement a long time. How does that make? Does it? How does it blow up? What happens to this term? It goes to 0, right? This term increases linearly with t, right? Which means this term we can also increase, right? And so what we end up with is 6 kt over m gamma t. Short times was ballistic motion. Long time is diffusive motion. Okay? So notice that in ballistic motion, r squared scale is t squared. Well, we know that's true because ballistic motion is defined by r being proportional to t. Right? But here, delta r squared doesn't go as t squared, it goes as t. Ooh. That makes sense? So this growth of the cloud outward, okay, doesn't go as t squared. It goes just as t. It's all right with everybody. What does that mean? Has a different scaling dependence. Okay, so we'll get to what it means. Okay, when we start to look at plots, because what it means is that if you plot delta r squared t, if you plot the mean square displacement versus t, you're going to see a crossover. Okay, it's going to go parabolic, and then it's going to go on a straight line. Right, and the parabolic part is your ballistic motion, and then it crosses over to a straight line, which is your diffusive. Cool? People okay? Yeah? All right. Let's slightly rewrite this. Let's put it back into this form. So we get rid of gamma. We put it back into general dimensions. And I want to be very bold. And I want to define something. Because capital D over zeta. Anyone know what this is? Yeah? The diffusion coefficient.
Atom model?
For me,
Isn't this using an Atom model?
we're using Zeta here.
Oh,
People actually switch them. So cool. This is a very, very famous expression. Okay, where the mean square displacement is equal to 2 times your dimensionality times the coefficient, which is the diffusion coefficient, times time. Cool. That's all right with people. Okay, because a lot has happened, actually. Okay, introduces a stochastic differential equation, and that actually gave us a whole different type of motion called diffusion. And because of the stochastic differential equation, we said we can't have the hope of solving for any particular trajectory, but maybe we can solve something on average. We found that the mean square displacement on average goes as this. And if this was ballistic motion, we scales as t squared. But now we have something that scales as t. It's fundamentally different. Cool? Diffusion, different. It's new own type of motion that we're going to study for a little bit, okay? Because it's very interesting. It's also very important, okay? A lot of things in your body are just kicking around due to thermal chaos, okay? There's also something very interesting buried in this relationship here. Okay? So from this relationship, we are saying, okay, we don't have a particle moving in a particular trajectory, but over time, if you were to take a whole bunch of them, on average, their square displacement from where they started will be non-zero. And we can characterize how this cloud is spreading by a constant, which is the diffusion coefficient. Cool? Good with that? The diffusion coefficient, we're saying, is equal to kT, which is the thermal energy, over zeta. What's zeta?
Drag coefficient.
It's a drag coefficient, right? Friction coefficient. This is kind of weird because we had two different terms in our differential equation. Right? We had a random term, and the random term is what gives us diffusion in the first place. And we also had this damping term, which was just that the water slows down if the particles go in some direction. And now we find out there's a very trivial relationship between the diffusion arising from the random term and the coefficient of the damping.
So it's just the ratio, how much you're getting hit versus how much you're slowing down, kind of thing.
What it means is that there is an intimate relationship between our random term, let's call it D, which is the source of the fluctuation, and our drag term, which is the source of our dissipation. Okay? So these two terms are not independent of each other. We can't change this one without changing this one. Okay? There's a fundamental theorem that links these two. And that fundamental theorem, fluctuation dissipation. Okay? I primed you for it. Right? So this is the first example we'll see of fluctuation dissipation. Okay, can anybody give qualitative insight into why this fluctuation dissipation theorem might be so? Why is it that the random term is somehow coupled to the drag term?
Well, it's not from the same place. You're moving in a medium and without acting against you. Sometimes they give you energy and sometimes they take away.
Right. Good answer. Any other answers? insights, ideas? There's another way of looking at this. My favorite way of looking at this is this. When we were talking about this, we said, okay, when we just isolated the movie to one particle moving around, we said, okay, well, it's obvious there's a random term, right? Things are kicking the same and it's moving around and swinging randomly, right? And then I had to motivate you to try and come up with the second term because it's obvious. And I said, well, what if we were applying a field to the system, driving the particle through? The effect of the other particles would be just something, right? So, if we're a particle in this system, okay, and we either get a large kick in one direction, okay, or we have some force that's driving us in some direction, the response of the surrounding medium is going to be the same, as long as that kick isn't too big. Okay? If your driving force is not too big, the system doesn't really know if this particle moving is due to some external field being applied to it, or if it's just the random kicks of the solenoids. Okay? So the response must be the same. And so the response to either a friction opposing directed motion or a friction term opposing the diffusion motion must be the same. Cool? Unless there's an intimate connection between the fluctuations and the dissipation. This is true as long as that force isn't too big. Okay? Basically, as long as a force that was inputting energy, that energy could be dissipated rather than through dissipation. Okay? If you have a very high force, putting in energy, you can heat up the whole system. You're in a very non-equilibrium system. Okay? But we can still consider a box of water with an ion in it to be an equilibrium system, even though all of this stuff is happening. Okay? And so the criteria that it be not too strong of force, it's part of linear response. Okay. Yeah, well, the thing is, so let's come back to when we first saw the idea of the word Langevin. What context could we see Langevin? It was a thermostat, right? Well, how is this going to act as a thermostat? We have a drag term there. We have a dissipation term. Okay, so even if we had an external field pumping in energy, we have this drag term that's going to take it out. Okay, so not only does this give us the randomness, but it also acts as a thermostat. Cool. How can we set the thermostat? Well, we can set the diffusion coefficient, KT. We can set the temperature. The temperature will go right in our equation of motion. And we can also set the friction coefficient. But when we set those two, that defines the diffusion coefficient for us. This is not an independent variable. This would not be an input to our simulation. Okay? It is a consequence of what we choose for KT. Cool. Due to fluctuation estimation. All right? Okay. When we come back tomorrow at 9:30 a.m., oh, and I do have a room, so I'll send out the room we're in. We're going to look at another way of looking at this, which is the Green-Kubo formalism. So we're going to look at velocity-velocity autocorrelation functions. And pretty soon we'll get to performing Langevin dynamic simulations, and then things will become a little bit more concrete because we're going to talk about how we can actually calculate the mean square displacement from simulations and to see if our general solution holds as well as our holistic limit and the mix. Cool. So that's where we're going to go. And again, the whole reason we're doing this is because a big part of this course is to introduce you to stochastic differential equations. And why do we want to know what stochastic differential equations? I thought this was a course about modeling systems with particles. Why is the stochasticity? Exactly. There's a lot of randomness out there and it comes into your systems. Okay? So it is a very handy feature to build in. And what we're seeing is that we can just include a random term in our equation of motion. However, we have to be careful with the character of that. Okay? Okay. See you guys tomorrow morning.